Hello, our current and future SACS users in Japan. My name is Bitna. I'm an application engineer at Bentley Systems. I'd like to let you know the latest version of SACS was released in February 2022. So, in this webinar, let me introduce the new features in the latest release. Let me start. There have been total 8 new updates. First of all, SACS server now accepts the elastic modulus reduction factor so that users perform the direct analysis method suggested by AISC. The next update on the server side is removing rigid body motion for statically indeterminate structures. We also add a new type of shell element to the advanced solver. This is to prevent the rocking effect of highly curved shell elements. As regards the pile-story interaction analysis, we have two new features for wind turbine structures. They are for the MonoPile analysis and the other for the analysis of the suction bucket structures. As regards the post-processor, the latest ISO code is updated, and a convenient feature is added to the SACS cloud computing. Let me explain these things in detail. First update is to apply a reduction factor to the elastic modulus. This is to comply with the rule suggested by AISC. The direct analysis method suggested by AISC replaced the effective length method. The effective length method is moved to the appendix, and this method came to this chapter C. The key points are to account for the secondary effect due to the deformation, and to predict the effect of the inelastic buckling due to the residual stresses in members. For the second order effect, as you see here, we already have some choices to implement it in SACS. If you select PF option, the second order effect is considered by updating stiffness matrix with full iteration. As you see, you have different level of choices. And now, through the update, SACS accepts the factor for the second order effect and also the factor to reduce the elastic modulus. So, stiffness matrix is formed with reduced elasticity. This is the first update. And the next update is detecting and removing matrix singularity. As we know, if structures are not properly constrained in space, it shows rigid body motions, meaning that we cannot solve the system due to the singularity. This is why we need additional boundary conditions, which is not real. For example, when we do lifting analysis, we usually model soft springs at the bottom of the deck to stabilize the matrix. But through the update, we do not need to do this anymore. If the singularity is detected, SACS automatically removed the rigid body motion, and structural analysis then proceeded. To use this feature, we need to go to the SACS settings in the SACS executive, then choose the advanced solver. The new command SLVOPT is added so that you can choose the method and parameters you want. This is the second update to the solver, and the next update is about the shell element for the finite element analysis. As we know, shell elements can have curvature, and it is known that theoretically, stiffening effects such as shear rocking and membrane rocking can occur if the elements have high curvature. The new update is to tackle this problem. SACS employs the MITC shell element that uses 4 interpolation points. Through this new enhanced shell element, SACS now provides a better analysis result of curved surfaces. To use this feature, we need to choose the advanced solver in SACS Executive, as we saw in the previous slide. The next update is about joint measure. As you may know, SACS has a modeling tool named Joint Measure. With this tool, we can convert the beam elements into meshed plates and also model some additional geometry at the connection that is not modeled with the beam elements. The tool is very simple and intuitive to use. Just clicking the connection and specify some basic information such as mesh density, then SACS gives you the meshed model. So with this tool, we can perform the localized analysis with the global model without external finite element software that consumes additional time and effort. For your reference, it has an option to comply with DMV rule to determine the size of each mesh and export some stress concentration factors for fatigue check. These are the features we already have, and the update is to create explicit stiffness for tubulars with joint measure. The stiffness are automatically added as members when the connection is meshed, as you see in the previous slide. These snippers can be created individually at the general orientation using the measure module, or as a longitudinal or lean snippers as shown here. Through this update, we can consider the additional stiffening effect very easily for more rigorous finite element analysis. The next update is for the analysis of Monopyle structures. As you may know, it is known that POI method for jacket type structure could underestimate the capacity of Monopyle foundation. This is because the method is developed based on long and slender piles that shows basically different failure mechanism with large diameter monopiles. To be specific, the traditional POI method considers the lateral, skin friction, and end-bearing resistance. But through PISA project, it is proven that monopiles have additional resistance such as moment resistance along the pile and the shear and moment resistance at the tip. Therefore, we update SACS to accept those additional resistance. One of the core ideas is to use Plaxis model to calculate such additional nonlinear springs for using SACS. For your reference, Plaxis model is the soil finite analysis software for monopiles. So the workflow is that the additional nonlinear springs are calculated in Plaxis model, then SACS imports those springs so that you can calculate the super elements for dynamic analysis, then do the structure analysis and code checking. This feature was available as a technical preview last year and now officially released. The next update is to design the suction bucket foundation. This feature is included in this official release from technical preview last year. A typical workflow is to model a structure including the FE model of suction bucket, then export super element which represents the stiffness of the jacket structure, and also exports the load vector and suction bucket model so that Plaxis 3D calculates a series of nonlinear springs that will be automatically imported back to suction bucket model in SACS. After importing a set of nonlinear springs, we can perform the any dynamic or static analysis to evaluate the structural stability of the entire structure, including the suction bucket. Let's watch the video. Here's the workflow I explained in the previous slide. After calculating the nonlinear springs, SACS import them and run the structural analysis. Here is the structural model built in SACS. And then after importing the model in practice, you will see this kind of picture. Then after the analysis, those kind of results will be exported in SACS format. And then here's a picture of SACS after importing the nonlinear springs. And after running the analysis, you can visualize the result and do some post-processing. One of our users, Fujian Yongfu Power Engineering Corporation in China, applies this SACS practice interoperability feature to their offshore wind turbine project. It was a huge project that has 62 turbine structures that have a suction bucket foundation. And the total capacity of the farm is 500 megawatt. It has the largest single unit capacity and the tallest structure in the world. But environmental conditions was not favorable. The water depth is deep for fixed wind turbine structures, and the design wave height is up to 23 meters. And also soil condition was very harsh. Using SACS practice interoperability, they include the nonlinear effect from soil for structural analysis, and also consider the properties of jacket structures when doing soil analysis, foundation analysis. In this way, they said they could save a lot of cost and also accomplish the world record by installing 5 foundations in series for 5 days. The next update is about the full plastic analysis solver. For those of you who are not familiar with SACS, let me explain briefly. SACS has plastic analysis solver named Collapse. It takes care of analysis beyond elastic range. It increments load, and at each step, the solver checks the deformations and plasticities of entire structure, then proceed to next step after updating stiffness metrics. This full plastic analysis module is normally used for accidental cases, such as blast or ship impact analysis. Few years ago, we developed new plastic solver with better numerical approach for post-buckling analysis. This plastic solver is called Collapse Advanced. The latest update is on this Collapse Advanced solver. Through the update, we can specify the ductility limit of plate elements and also piles. So, SACS assumes that plate fails if strain exceeds the specified ductility limit. With this new feature, we can do better plastic analysis with meshed elements. To use this feature, you need to go to the SACS settings first and then select the Use Collapse Advanced. The next update is about post-processor. As you know, ISO released a new version of 19902 in 2020. We added this code to SACS post-processor for both member unity check and joint punching shear check. The next update is about cloud computing. As you may know, cloud computing is supported in SACS, and through this update, this cloud computing can be monitored and controlled in SACS Executive, so we do not need to travel to other windows. Also, if cloud computing is not an available option to you, maybe due to this security issue, you can use computers in your network for multiple analysis. This is a grid processing, and it only consumes one license, even if the analysis run on multiple machines. So this is one of the choices, one of the options you can choose. This is all I prepared today. Thank you for joining our webinar. If you have any questions, please send them to me or Saikar. Thank you.